Suppose we know for the function f of x, it is true that for all x greater than or equal to 1,000, f of x is somewhere between 1 and 3. So we're not saying it settles down and actually, has well behaved, and then it's always getting closer to like 2 that's in the middle. We're just saying after a certain point, this function, if you graph it, it's it might do crazy things out here, but after 1,000, it's sort of stuck. It'll always be somewhere in here, but it might bounce around and do some silly stuff, kind of like sine or cosine or something like that. But what we're saying is eventually you can guarantee f of x always between 1 and 3. All right. So continuing on, determine whether this series here, the sum from n equals 1 up to infinity of 1 over n times the f of n, so taking the whole numbers n and plugging them into this f function, who we don't have a formula for, but we do understand sort of some of its behavior, determine whether this series is convergent or divergent. Okay. So we have an inequality given to us. Inequalities like this scream comparison test, but there's a few things to watch out for. One, we're not adding up f of x. So this inequality is not going to be immediately useful because we've got 1 over n f of n. So we've got to sort of manipulate the inequality and make it look more like the thing we're adding up. Another thing we have to watch out for is that this inequality does not hold right away. It holds after a certain point. After a certain point doesn't really concern series, though. Remember the theory that we know that we've learned. Right? If your series converges or diverges, that has nothing to do with the first term, the first trillion terms, the first Google terms, however many you go out. As long as a tail converges, the whole thing converges. As long as a tail diverges, the whole thing diverges. So the first thing I might do before messing with the inequality and bringing in the comparison test, which we know pretty much needs to come in, we might say, well, let's make sure that the inequality applies so that we can start constructing things and working with the comparison test. And so we're going to split to a tail. Okay. So let's say here. Oh, clicked the pen twice there. All right. So first thing I would do is I would say, look, we know that this infinite sum here, the 1 over n f at n, converges or diverges exactly when the sum from n equals 1,000 up to infinity. Why did I choose 1,000? Because we're told that inequality starts at 1,000. If they had said x greater than 1,000, I'd start at 1,001. Okay? Or if you want to really be safe, start at 2,000. It honestly doesn't matter, but the point is I need to go far enough out so that I can start working with that inequality. So we say, all right, let's just look at a tail. So the convergence or divergence of this is the same as the convergence or divergence of the thing we're talking about. Okay? Crucial step, because you cannot just jump in with that inequality because you don't know that it's true. In fact, for all you know, for some early values of fn, things the fn's might be negative, in which case you can't use the comparison test as we're about to see it because it requires positivity. Right? Subtle little thing, but yeah, it could happen. So we shift around, we say, okay, so now for all our values of n that are greater than equal to 1,000, which are the only values of n that we're concerned with now, we're told that f at n is less than 3, greater than, it is greater than, yeah. That's not, well, let's just double check. It doesn't really matter if it's less than or equal or greater than or equal, but it's good to ask. Okay, yeah, it is less than. So we've got this inequality. So what do you do when you've been given an inequality or you come up with sort of an initial inequality, but it doesn't quite fit with the sequence you've got? You want to slowly take this, rearrange it, rewrite it, use your knowledge of inequalities to make it look more like the ANs, the sequence you're adding up. Okay? So we've got 1 less than f at n less than 3, and we want it to look more like 1 over n f at n. How could I do that? Well, I suppose we could multiply both sides by n to get the n with the f at n. That's an option. We could take reciprocals to get that f at n at the bottom. There's lots of different options. There's no one correct way to start these things off. But I might say, all right, so we know this for n greater than or equal to 1,000. Not that that's a big deal. I might start off by saying let's just sort of do reciprocals. Okay? Now, when you take the reciprocal of positive things, the order switches, right? 2 is less than 5, but 1/2 is bigger than 1/5. So the inequalities flip around. 1 over 1, of course, is just 1. So this is also true, right? Because all these numbers are positive. How do you know the fn's aren't negative? Because we know they're bigger than 1. How do you know the fn's aren't 0 and you're not divided by 0? Because the fn's are bigger than 1 at this point. Okay? So that's guaranteed. So this is also true for n greater than or equal to 1,000. And this is looking a little more like my sequence. What's missing? Well, we're missing an n. So how about we come along and divide by n everywhere? I'll say 1/3 over n for what I'm about to do. So great. We've got 1 over n f at n. We do want to be careful. The n's were positive, so the inequalities didn't have to switch. If n was negative and we divided by it, these inequalities would flip around. So you got to be aware of that, because subtle little things, you might think you're building up the right inequality, but oops, it just didn't quite work out. So this is also true for n greater than or equal to 1,000, right? This one, we can do the reciprocals, and it changes the order because everything was positive. And this one here, divided by n is positive. Okay? N is definitely positive. It's at least 1,000 right now. Okay, so when I look at this, even though I don't know my fn's, I know that the sequence I'm adding up is less than the harmonic sequence, but it is bigger than a multiple of the harmonic series. And the harmonic series, harmonic sequence, but the harmonic series adding up all those numbers diverges. And so any multiple of it, other than a multiple of 0, will also diverge. So that gives me my in with the comparison test. We're going to use this inequality. But we do have to dress it up and justify things. So I'd say, look, well, let's get a separate piece of paper. Let's say, hey, notice that since the harmonic series, which is well known, you can just go right ahead and quote it, the harmonic series 1 over n here to infinity. Get rid of that little dot that I accidentally put there. So since this diverges, now you got to watch out, because we're not dealing with starting at 1 for our sequence here. We're starting at 1,000. So because the harmonic series diverges, I can confidently say that any tail of it diverges. And so any multiple of this divergent thing also diverges. And that's how I can bring in the 1/3 over n. So this is divergent. And since we've already said that for n greater than or equal to 1,000, we were able to show that the sequence we're trying to add up is bigger than 1/3 over n. If the smaller thing diverges, grows too large, then the bigger thing diverges. How do you know? Well, that's what the comparison test tells us. This is by comparison test. The sum from n equals 1,000. Got to be very careful, right? We want to be precise. We want to be accurate. But this also diverges. Okay, so that came from the comparison test. And then the final thing to say is, well, this is a tail. If the tail diverges, the original thing diverges. So we'll say since this tail is divergent, so is the original that we were asked for. 1 over n, f at n. Even though we don't know exactly how the f function behaves before 1,000, it can be wild, it can be crazy. You got to remember, as far as an infinite sum is concerned, we don't care. It's all about what happens eventually. So there we go. This is, in fact, divergent.